Hello and welcome. Today is the 10th of July. You have to pardon my usual cough at the moment during this video. It's a choice of either doing the video or not doing it to avoid this annoyance. But there's a title, A Vicious Cubic. Okay, what is, first of all, the maths required behind all of this is actually year 12 maths. So it's actually quite low level knowledge, but of course quite a lot of difficulty. This is a standard result I've seen it many times in my mathematical career, and this is what it's actually saying. I'm going to write it here somewhere, and then we are going to try to see how to prove something like that. So here we have a cubic, and the cubic has equation x cubed plus bx plus q is equal to 0. P is a negative number, negative real number. P and q are constants, real constants, where p is in fact negative. So that's a fact. Second fact, this equation has three distinct real roots. And the third is not a fact, is to prove now. If we have this cubic and it has three distinct real roots, to prove that, in that case, 27 q squared plus 4 lots of p cubed must always be negative. Pardon me, so annoying. Pause the video if you wish to have a go and see if you can make a start with that. The start is not obvious at all, unless you kind of seen this or you're a genius. I'm certainly not a genius, and when I first came across this kind of question, luckily I had the answer. It's a very long time ago when I was learning maths, so I didn't really give it enough to try it. But this is how you have to, where's the starting point for that? We have three distinct real roots, so the cubic will look something like that. I'm not drawing a y-axis here. 1, 2, 3 roots. What's the consequence of that? Well, suppose he only had one. So he had the same shape, but he looked something like this. How is that different to that algebraically? Of course, in the picture we can see what's different, but what difference does it make? Well, this is what we need to observe here, which is not easy to spot. If we have three distinct real roots, 1, 2, 3, then the y-coordinate of the two stationary points will have opposite signs. In other words, I don't know, let's put some numbers so we can actually see it. Let's say this point here has coordinates 4, 10. This has coordinates, I don't know, 9 minus 5. Definitely, the y-coordinates will have opposite signs, 10 and minus 5. So when you multiply them together, the y-coordinates of the stationary points, you should get a negative number. So this is the plan. Well, here, for example, that's not true. It's quite obvious not true. For example, if that was a 410, again, and this was, I don't know, a 2, 3, they have the same sign because both of these are above the x-axis. So this is what this question is all about. It's about stationary points. It's about differentiation and some kind of like not so nice algebra, perhaps. So let's write this in function notation. X cubed plus px plus q. And let's differentiate it. All straightforward stuff so far. Set it equal to 0 to look for stationary points. And of course, 3x squared will be minus p. Keep in mind, of course, p is negative. So this is in fact a positive number, because you might be wondering, 3x squared is equal to minus p. I've got a problem. So x squared is minus p over 3. So your x would be plus or minus the square root of minus p over 3, where p is a negative number. Let's underline that so it's there for us to see. And now we need the y coordinates. Remember, these are not true, just put some numbers. So basically we found the x there and the x there. So the question now is, what's the y coordinate? And I'm going to do it in one go because it's actually easier, because I got plus or minus. So f of plus or minus, so I'm getting the y coordinate from here. Minus p over 3. I'm going to put full workings. This type of questions always cuts me, and it can cut you very easily if you're not careful. Probably I say that and it cuts me anyway. So that's the cube. Okay, and then we go plus p, bracket, plus or minus square root of minus p over 3, plus the q. So that's the y coordinate. We need to simplify that. Now cubing a plus or a minus, it returns the sign. So it's going to be plus or minus. And if we cube that, first of all, if we square it, it will release a minus p over 3. And then, of course, we're going to have just the square root of minus p over 3. That's from this quantity here. And then this item will be a plus or minus p, that's this p here, square root of minus p over 3 plus q. And now that's where we have to be careful with this plus or minus and this minus here. Now it will change into a minus, so the plus times the minus will go minus, and then the plus underneath. And then we have 1/3 p, 1/3 p square root of minus p over 3, plus or minus p square root of minus p over 3. And these terms are exactly the same, just have bizarre signs, plus q. So let's see what we have. If we have the top version, so we're going to have minus 1/3 plus 1. So that's going to be a plus 2/3 p minus p over 3. So because notice this is just a lump, call it x. And the p times x, you call it y, all of this call it y. So you got a third y and you got a y, but you have a minus and you got a plus, a minus 1/3 plus 1. So you end up with plus 2/3. If you go for the bottom one, you're going to get a plus 1/3 from this bit here, minus 1, so you're going to get a minus 2/3. So it's going to be looking something like that. So plus q. So the y coordinates basically are in fact the x coordinate. It doesn't really matter the x coordinate. All I want to put is, of course, that the y coords are, which are stationary, of course, 2/3 p and of course the other one is going to be exactly the same, but with a minus at the front. And remember now, what are we trying to prove? We're trying to prove some kind of inequality less than 0. And I did mention if one is above the x-axis and one is below the x-axis, the product of those two y coordinates, of course, should give you a negative number, which of course, I don't have enough room to do it here. But of course, we got 2/3 p bracket minus p over 3 plus q, multiplying exactly the same thing. I should have written it back to front so you can see the difference of squares better. 2/3 p minus p over 3 plus q. It's a difference of squares, so I've written it as q plus that, q minus that, so that is less than 0, fact. And when we do the difference of squares there, we're going to get a q squared minus, and I'm going to put it in a bracket, 2/3 p square root of minus p over 3 all squared is less than 0. And I think the result should follow within 2 lines. I run out of space, they're very annoying. I have to make some space up here. So this will now give us a q squared, and we're squaring this quantity, so that's going to be a 4/9. So it's going to be a minus 4/9 p squared. That's up to here. And then of course we're squaring this quantity here, and I want to use a bracket because of course when it gets squared it's going to be a minus p over 3 less than 0 q squared, and it's going to be a plus, minus times a minus, a p cubed, that's this bit here, and then we'll go 4 over 27 is less than 0, and of course since 27 is a positive number and we don't have to worry about anything else, 27 q squared plus 4p cubed is less than 0, and of course the result has been proven. A very different question. All year 12 maths, I mean, if you look at what was involved in this question, yes, I mean, the difficulty was at a different level, but all you had to have is knowledge of cubics, the shape of them and the graph, calculus, just basic differentiation of polynomial, and just finding stationary points, and then of course how to relate all this kind of stuff into some result that we're trying to find. I hope you enjoyed it, and I'll be signing out, and I will see you real soon with more videos on maths. Bye for now.